All right. Okay. More technical. Page down. No. There we go. Okay. Great. Okay. So to start, I think this is an interesting quote. Time is limited, so I won't dwell on it. But if you're working on like bringing more nonlinearity into classic macro models, people were already thinking about that back in 1979, and I think that's interesting. Okay. So where I see most of the talks today fitting in is this very general paradigm of machine learning for science, which is described here. This is something that's been highly successful across all kinds of different fields, especially in the natural sciences. Seems like it's also going to be successful in economics. I certainly, if there were prediction markets in papers, which there should be, I would be long all of your papers. It seems like a great line of research. Something you could do instead of the computational techniques you've all described for solving Bellman equations is to use deep reinforcement learning, which is also a totally different paradigm for finding solutions to Bellman equations that has not been applied that much in economics, but has been really successful on a lot of extremely challenging real world problems, in particular challenging real world problems where you can't clearly describe the environment or the state space or the rewards you're dealing with. All you need for deep RL is black box access to all that. So you don't really have to understand it. You just have to be able to code it up. That opens up some interesting new modeling possibilities. It's a really tempting idea. It seems like a natural fit for economic modeling. But if you want to do that, it turns out you run into a lot of problems. Problem classes here. Modeling choices, software engineering challenge, and how do you validate a solution given that these methods don't come with convergence guarantees? So some modeling choices, like classic modeling requirements for economic models, work okay, like the no Ponzi constraint, which you've heard about some today. Others, like market clearing, are more challenging. So the no Ponzi constraint is basically just constrained RL. Market clearing, it's not obvious how you should do that. It's a joint constraint imposed on all the agent's policies at once. That's not an easy thing to do in the RL paradigm. A few different papers tried various different things there.
Wait, just,
yes.
I know you're going fast.
Yes.
So Marlon was able to incorporate the market clearing constraints. So that's because he was doing kind of a centralized approach, and yours is decentralized. Is that why you're saying
this is like classic RL, like we're going to do like in NURBS.
But like
versus this
individual agents, and that's why they're all learning independently.
They're all learning policies. Yeah. If you're doing this RL, these NURBS style RL algorithms, it's not clear how to enforce market clearing.
I think in Marlon's one, the agents know the structure of the income. That's why they can impose that. Whereas I think you're going to have the agents who don't know the structure. So
it's this ML for science paradigm, like physics informed ML, versus just using deep RL like people use for game solving work. Okay, there's various things you could try. None of them are completely satisfactory in my view. That's kind of an economic modeling constraint. Also, if you try to do this, you're going to run into a lot of software engineering challenge because you need your simulator to be extremely fast. In particular, if you're thinking about taking some off-the-shelf simulation that you like that's accurate and wrapping it up with an API and having your RL policies interact with it, that's probably going to be very painful for you. It's not impossible, but if you're doing it, you should feel nervous. And then the last thing is if you want to validate your solution, these RL algorithms don't come with convergence guarantees. And in my view, the best thing, though not completely satisfactory, is to do what people do for game playing and just measure exploitability by training one agent's policy at a time and see how exploitable the equilibrium is, how much they can improve their reward. So here's the takeaways. That's the extremely abbreviated version of my talk. And now we can all go eat plant pizza. Oh, and I also want to highlight. Yes, they were on the really fast. Yeah, so you need this interplay between the very practical nuts and bolts of making RL work, but also like good taste and good economic thinking for what things you can get rid of in your model, what things you still need, how to make an economic model that's economically convincing, but fits into this Markov game paradigm.
So this is an engineering endeavor, what you're saying.
Engineering, but also good modeling taste. All right. And then a paper on a very different problem, but it's really well written and is appearing at EC this year, that I recommend reading and going to see the talk. That's it. And
We got it, that's it.
Well,
Yeah,
you can take questions. I mean, if you wanna leave, but you stayed all the way at the end, so you don't wanna stay.
Just go back to your description, so,
Where,
so you're describing part of what I call fictitious play, right? Where I fix the other agent's decisions and then I play against them and I gradually learn.
yes,
And I guess we have one class of fictitious play algorithms where the agents know the structure of the economy, like U-chain sort of stuff. And then we have other people that try to do these fictitious play algorithms where I don't know anything about the structure of the economy, which I guess would be closer to.
I would, even those
Yeah,
are like, usually when people talk about fictitious play, if you had some regularization, it's usually a nice convergent algorithm. This is more like getting the best approximation you can of a best response by just running deep RL. And so you're in a world where there's no hope for convergence guarantees, but you can at least empirically measure how exploitable you are. And this is what people do for like when they use deep learning for game playing, like poker and things.
Can I, so maybe this is like a very super basic question,
Mhm.
but it's something that I've been trying to think about how to apply to economic models and like how I've been trying to set things up. Reinforcement learning like properly refers to this model-free approach where you have this black box simulation that all you can do is simulate forward once, right? But, well,
You can hold it back.
Yeah. So like what I'm wondering is, is there like a good standard terminology for black boxes that can do like one more, like a black box with one more button on it? Meaning, for example, suppose you have a black box, you can simulate forward through it, right? And you can also like make a checkpoint of the state before you use the black box and roll it back and simulate through it many times.
It makes sense as a concept, right?
I mean, this is like the fictitious play of AlphaGo works like this, right? You start from a single point and then you kind of evaluate a state by simulating forward several paths from the same starting point. Yeah.
I just want always reinforcement learning. Right.
Usually that would imply you're learning the model though.
Yeah, the point is that you are not allowed to know the model, you're allowed to have one specific function of the model while still treating it in other senses as a black box. Like you're not allowed to differentiate through the box, but you're allowed to reset the model to the input of the box.
I think this is the question maybe relates like, is your simulator of your environment, whether if you have first order access to the simulator or zeroth order access, there's work on this from like,
It's like, what's the name?
Yeah, I changed that.
High chains. Right, yeah, on differentiable simulators.
But in general, for AlphaGo, they just do like Monte Carlo
right, that's
research.
true, yeah.
But no, I mean, this is nice, like, I mean, in general, with the differentiable simulator, you have a black box that gives you the output and the
Yeah, so
derivative.
the assumption generally, they go like, if you have a zeroth order simulator, it's like you only get the actual values.
Yeah.
If you have a differential simulator, you get like the values plus the gradient. So people will set up those, if you look at like a very precise technical, theoretical paper, they will say, we're assuming like the Nurowski model of an oracle, when we're getting calls and stuff like that. But like a lot of the RL papers are not that precise, so you won't see that, and they're more just like zero order. It's more about the oracle simulation aspect. That's probably the language I would look at. Yeah.
I guess the thing that you're proposing is not too far from having a model, right? Like if I want to access any state, I could just like set sample until I get to that state.
Yeah, it's like being rigorous about how much access to the model you have, which is useful because it can help you define the generality of the solution algorithm.
But what do
Right.
you mean sample until you get to that state? I mean, you have many states.
Yeah,
You
that's
may- Right, that's the problem. So you can assume more information, but your state space is so large that you still may never see states.
I mean, if you can back up, you pretty much have to have like access to the conditionals to the model, right? I think this intermediate kind of maybe never occurs.
But like when we solve economic models, sometimes we use lots of information about the model, right? Like if you train a neural network to approximate the policy function, right? You are like in some sense tailoring the solution method to the details of the model in a way that, the idea of defining a model in terms of having a black box that gives you only certain outputs, right? In principle, is nice because you can kind of reuse the same solution method and change some details of the model and be precise about how much you can change the solutions of the model while retaining the same
What,
solution method.
but what I'm saying is if you're able to rewind by one step, I mean, typically that means that you have access to some sort of conditional distribution, which also means that you can start wherever you want. So I think the situation where you're only able to rewind, not able to set up some arbitrary.
Okay, sure, you can set up an arbitrary
prefixes,
situation,
almost kind of never occurs.
but you can assume that you can't, for example, differentiate through the black box.
Yeah.
Right. But you can start from an arbitrary starting point, which is there's a number of different possible like abilities that you can assume the black box has.
Yeah, okay. I'm just saying that at least in the way that I think about this, usually either you only have this kind of pure sampling based access, or you have the ability to start from some sort of state and run your model forwards, and that's usually, then you're doing some sort of model-based planning, right? And there's not usually this intermediate case where you can go back up by one step, but you can't.
Okay, no, that makes sense.
But yeah, you have to just say inference, if you're able to back up and get this, distribution based on the conditional, you've got to be able to do it.
Yeah.
Jesse has his hand up.
Jesse, can you talk? Like, can we hear you? Can you try?
There's a lot of questions.
Hello? Oh, we can hear you. Yes. One sec. I hear. But can we hear you?
There's something, could you please share the screen on Zoom? That's one of those. Okay.
I think that was our.
How do you hide?
No, we fixed that. No, we did fix that one. We fixed that one. Let's go to participants. Oh, maybe he left already. No, were you there?
There's Jesse.
Oh, wait.
Allowed to talk.
Okay, here you go. Just, can
Jesse,
you
can you
talk?
talk now?
Yeah, can you hear me?
Yes, we can. Sorry about
Oh,
that. Thank you.
great. This is really great, and I have a big question on the sort of a bigger picture question on the RL is how should we think, like, what is the purpose of the multi-agent RL? So what is our goal here? Are we using this where we think that in the limit, this would approximate human behavior? Are we thinking about this in the transition dynamics? Like I guess one of the things is I'm not sure where we should be thinking about applying this, because we know that these things often learn very slowly and often go to all sorts of weird equilibria. So I just love your kind of guidance on where you think these are most applicable for economists.
Yeah. So I had a slide on that I skipped, but now I'm really, is that, yeah, how do you, there we go.
They can see that.
We can.
Yeah.
So I think this is the dream. This is like why this would seem like a good idea, even though you're about to do deep multi-agent RL, and so your life is going to be kind of bad. That you could put whatever weird stuff you want in your model. You could have little dudes running around playing a video game, fighting each other, whatever bizarre stuff you want. It's a huge amount of modeling flexibility, but you still have agents who are behaving rationally and optimizing some utility functions. And so you get around at least some of the criticisms of agent-based models. And
I think
so that's a very tempting idea.
I think what Lucas would say in this situation, I'm just guessing here, is that where the rational expectations revolution started was that agents had an internal model which may be wrong of the future. It was not completely experiential. And in that sense, multi-agent RL, as long as it's backwards looking, unless you have some model of your opponent which is not experiential, I'm not sure that Lucas would be happy. Now, it doesn't mean he needs to be happy, but I think this is sort of the limitation on multi-agent RL from macroeconomists. And I could be wrong, but this is just sort of a general impression a lot of people have.
I mean, if you're at equilibrium and everyone has a policy that satisfies a bunch of Bellman equations, is that not enough?
If you're talking about a long run, yes. And Sargent, Evans, Honkapoya, a bunch of people looked at these sorts of learning models, and they looked at the long run equilibria, and it ended up giving equilibrium selection and all these other things. And in that sense, I think these people would be fine with that. But I guess that's the question: is the goal the long run, or do we really think that we can simulate agents in this way without them having an internal model?
So this is another point I skipped, that I don't really want to model an agent that's learning. I just want to use these RL algorithms as a computational tool to get out policies that are optimal according to some reward that you've defined.
I
So
mean,
maybe that partially answers the question.
Are you saying you're interested in the long run? Is that what you said?
I guess so. I'm interested in optimal solutions in whatever markup game you want to click on.
I mean, you're saying the agents are acting as exactly as an optimizing agent who had an internal model would act,
Yes.
because they're acting optimally in the same way that indistinguishable from a forward-looking actor.
But I think
Right.
the problem that like also Jesse's bringing up here is that those algorithms are not guaranteed to converge to a solution concept, so. From that point of view, there's like a predictive issue, I think, right? Like, I think there was some work on being like, on talking about, you know, like if you run these algorithms or no regret algorithms, you can see them that way. So the solution concept is essentially some like no regret policy. You can think of it that way, but in general, there's not a well-defined notion of equilibrium or something like
There's not
that.
a hard convergence guarantee. I guess that's
Right.
one of the problems here.
that's the thing.
When are you convinced that this is converged enough to call it some kind of meaningful equilibrium?
Which becomes a predictive issue then if you fit these models on data and you wanna
Right.
make a prediction. I think maybe
At the
that's.
same time, inverse RL doesn't work somewhat.
Right, yeah, I do agree, bias.
All right, I
Thank you
think
so
we've
much.
kept everybody
Oh,
long
you
enough.
got another question? I don't want to trap everyone
Oh,
here.
please, yeah.
Chris, if you wanna say a quick word, because everyone wants to get out.
No, no.
Can you guys hear me okay?
Yes, we can.
Okay, first of all, just thanks everyone for the presentations. They were awesome. Just a last quick comment on on when we know it's a solution or and all that. Couldn't we still use the standard accuracy checks that we use in models currently? If we were to solve a model using say DeepRL for the individual agents, for example. I mean, if we know that much about the model, can't we still check that the policies solved for using RL kind of satisfy those conditions? Like, wouldn't that be kind of a first pass?
Yeah, I think that would definitely work, but the hope is that you could cook up some kind of really weird model where you could no longer do that. But still use RL to get some kind of rational behavior out. So then in that case, you wouldn't be able to check it.
Yeah, okay, that makes sense. Thank you.